Here I'm gonna cover hydrogen-like ion, which is the Bohr's atomic model of hydrogen, but in this case it would be the hydrogen-like ion case. This problem is taken from OpenStax 8.6, problem 96. The ion beryllium 3+ makes an atomic transition from an n equals to 3 state to an n equals to 2 states, and it is asking us to find the energy of the photon emitted and the wavelength of the photon. So as I define the problem, I first identified that beryllium 3+ have 4 protons and 1 electrons. And because it has 1 electron, this means that this is the hydrogen-like ions. So the question said it transitions from n equals to 3 to n equals to 2. So as I draw the energy diagram here, I'm indicating that this electron goes from n equals to 3 to n equals to 2. So this is the equation that we have for hydrogen-like ion, and because beryllium has 4 protons, so m would be equals to 4. Oh, sorry, m would be equals to this number of state, and z would be equals to 4. So here, if I plug in that I'm finding the energy of the third state, n is equals to 3, so this would be 3 and this would be 4. And then same thing here, and then when I calculate the E3 and E2, I just have to calculate the transition from 3 to 2, which is 30.2 electron volts. And if I convert the energy to lambda, then I have lambda to 41.1 nanometers, and that would basically conclude all the questions, answer the problems. But I want to do a little bit of extension here, is that as I draw the energy diagram of beryllium 3+, here I have E1, E2, E3, I have E4, E5, and all the way to E equals to infinity. And when it is, it's n. When it is n equals to infinity, that means that the electron of the beryllium 3+ is ionized. So it would be beryllium 4+, which is, yeah. And so if I just plug in all the values here, we have E1 is this one, and E infinity would be this one. So I set here a 0, and then go here, as illustrated from the energy diagram. When it is n equals to 1, it is called the ground state. So here, the question is asking for an emission, which is from n equals to 3 to n equals to 2. But in order to have such an emission, we need to have absorption, so that this electron is here at the n equals to 3 state, because it is not in the n equals to 3 state, it is unstable at n equals to 3. So electron is from the ground state, it would jump up to n equals to 3 or higher energy state, and then go back to n equals to 3, and then to n equals to 2. So there are actually 2 absorption, which is via collision or photon, which is quantized. What quantized mean is that there has to be, when there is a photon here, when the electron is absorbing the energy from the photon, the energy of the photon has to be exact amount of the energy jump from n equals to 1 to n equals to 3. And as calculations show here, the energy has to be 193.4 electron volts if it is photon. But if it is via collisional, maybe another neutron, a proton, or electron was hitting this electron, then that, because it has mass, so it would have kinetic energy. So some of the energy could be transferred to this electron, which would excite to n equals to 3 states or higher, and the remaining energy could be the kinetic energy of the matter. So the energy of the electron, proton, and neutron could be higher than this electron volts, but not really exact. But it could not be lower, because if it's lower, then it doesn't have enough energy to excite the electron. And this is basically explaining the Bohr atomic model of hydrogen.